In this lab, the motion of an object was observed in order to gain an understanding of Newton's second law. An object was recorded after a net force was applied. During the video, the object was moving in only one direction with a constant velocity. A computational model was used as a control, and this model provided hypothetical data to compare with the recorded experimental data. The provided starter code was edited to best fit the conditions, and the momentum principle was applied in this code. Both the experimental data and hypothetical data had a linear slope when graphed, and they followed each other very closely. On this slide, we have a graph of experimental versus model, where experimental is blue and model is red. We also have data from tracker and a position and time table from GlowScript, as well as the video.
I think I'm ready when you are.
Newton's second law best explains the conditions of this experiment. After the object was pushed, it was allowed to move a specific distance before it was stopped. And while the object was in motion, it had a net force of 0 because it was not experiencing any pushes or pulls. And Newton's second law can be written in many different ways, but it essentially tells us how the mass of an object and its velocities at different times are related to its net force. In this experiment, the object's motion was isolated to one axis, providing a simplified example of the relationship between motion and time. Friction was assumed to be negligible in order for the object to experience this net force of 0. And again, Newton's second law states that the net force acting on a system is equal to the system's change in momentum. Moving on to experiment and code, the system is the cart, while the surroundings are the air, the track it was on, and the people who pushed and stopped it. The cart had an initial position of negative 0.007 in the x component, 0 y component, and 0 for the z component. To set the cart in motion, an initial force was applied in the positive x direction. After the force was removed, the cart had an initial velocity of 1.8515 in the x direction, 0 in the y, 0 in the z meters per second. The cart started at 0.3 meters and stopped at 1.4, traveling a total of 1.1 meters. The provided starter code was copied into GlowScript. The net force factor was changed to 0 for all 3 components since the change in velocity experienced by the object was 0. The time was changed to 0.3 seconds because that was the amount of time it was tracked for with the tracker function, and the weight of the object, initial velocity, initial position, and code for the momentum principle were adjusted. The momentum principle was edited to be more general, and the delta t was also decreased since the time interval was so small. And this decrease in time was just to help the model be as accurate as possible. The experimental and hypothetical data form linear slopes. A linear slope on a position time graph represents constant velocity. The line representing the model lies slightly below the experimental line. This might be because the object was still experiencing a slight acceleration from the initial force during the period it was tracked. During the experiment, the object was given a large initial force, resulting in a short video. The object was tracked for a small time frame because the object traveled too fast over too short a distance. In future experiments, a smaller initial force will be used. If the x-axis was flipped in tracker to be in the negative x direction instead of positive, then the velocity of the cart would remain the same, while the object would travel in the negative direction instead of positive. In this case, no forces are acting on the cart while it has a constant velocity.